Okay, so we're here in the 12th lecture in our course on real analysis. And ultimately, our next goal is to understand the notion of continuity of a function of the real numbers to itself. Now, the book, being a math textbook, is in perfect logical order, which means it's in reverse psychological order. So the next topic that we tackle is not actually continuity directly, but a logically precedent topic, which is the study of certain kinds of subsets of the real numbers. And this is because certain properties of continuity really depend on how continuous functions interact with certain kinds of subsets of the real numbers, specifically intervals and closed intervals. And so the definition of continuity itself involves the notion essentially of an open or a closed set in the real numbers. And then certain important theorems, like the fact that a continuous function on a closed bounded interval like this achieves a maximum, that's related to how continuous functions preserve compact sets, and the intermediate value theorem is related to how continuous functions preserve connected sets. So we want to understand the notion of continuity and be able to prove these theorems. And so the swiftest and sort of most insightful way to do that is to understand first these notions of open, closed, compact, and connected subsets of the real numbers. So that's essentially what we do first, and then so we do that first, we understand these notions, and then we move on to talking about continuous functions. It might be more psychologically natural to start thinking about continuity directly, and then deal with these notions as we sort of run into them, but that is not, alas, how the book and most standard textbooks go about this, because it's sort of logically more congruent to do it this way. So anyway, that's the plan. So just a little bit more about my plan before we move on to the material proper. The text only discusses the case of the real numbers, and so these notions of open, closed, compact, connected for just the real numbers. And I think this is kind of a shame because the sort of abstraction that's involved in understanding these notions just for R is in a way is kind of wasted, because R is comparatively a simple has a comparatively simple structure as a set. So it's not that much more burdensome if you're going to make a study of these sort of abstract notions of open, compact, connected sets, to just study the same notions in the general Euclidean space Rn, rather than to just restrict yourself to the real numbers. So I think to really make it worth our while to study these what are called topological notions in the real numbers, we're going to study them in general in the setting of Euclidean space Rn. Because once we do very little work to extend ourselves to Rn in the beginning, and then all of the work we do after that applies to Rn generally, rather than just the real numbers. So with very little work in the beginning, our yield is much greater ultimately by talking about Rn in general. Okay, so we'll start by just discussing briefly, how to talk about Rn. So we'll talk about some, how to talk about convergence of sequences in Rn, and it's really just becomes a special case in a way of our discussion of sequences in R. So not all that hard to extend ourselves into Rn, and then we'll start discussing these topological notions. So this week we'll be discussing notions related to the idea of an open or closed subset of Rn. Okay, so that's the outline of what we're going to do. Okay, so starting with Rn then. I presume none of this is really new. Elements of Rn are just n tuples of real numbers. Right? So we have x and y, two different n tuples. We can add them just by adding component-wise. Right? X1 plus Y1 is the first component, Xn plus Yn is the nth component. We have this familiar sort of intuitive picture of X plus Y as this sort of parallelogram force law for addition. The sum is just the diagonal of this parallelogram of X and Y. We think of X and Y as vectors sort of emanating from the origin 0, 0, 0, etc. in Rn. And then we also have the notion of scalar multiplication. So any scalar in R, any real number, we can multiply by a vector by just multiplying it by all the components uniformly, and you just picture this as call it a scalar because it just scales your vector, right? Sort of in the same direction. And then we have subtraction, right? So we can subtract vectors. Then x minus y is just x plus negative y, right? So negative y being defined this way, and then we have addition defined. So this is a derived notion from the previous two, and you just have just think about it as subtraction, sort of subtracting component wise. And again, we have a kind of parallelogram law here. This is the other. If we sort of look at compared to this picture, as the other diagonal of the parallelogram there, sort of measuring the, so it's a vector going from tip to tip in this case. Okay, so those are the basic notions. And what we want to do is study convergence of sequences, and so we need to be able to measure the distance between two vectors, right? So in R, we just have, if we have real numbers x and y, right, the distance between them is just the absolute value of x minus y, and so we just need such a notion in Rn, and that's what we move to next. Okay, so the distance then between two vectors or two elements of Rn is just given by this expression. So the distance between x and y, it's the square root of the sum of the squares of the components of the difference. So we just look at the, right, so you just kind of think about your x and y. Here's the vector, which is sort of measuring the separation of them, and then we compute the length of that vector using essentially what we're doing is using the Pythagorean theorem. So we're taking as our sort of standard for distance measurement for n equals 2 to be given by the Pythagorean theorem, and then taking sort of the obvious generalization of that, right? Because if in n equals 2, if you have you point x here and point y here, the distance along there is just given by the Pythagorean theorem, right? So you compute the square of this, which is just the separation between the first component of x and the first component of y, and the square of the vertical separation, and then you take the sum of those two and you take the square root, and that gives you the length along there. Okay, so we're just sort of taking the obvious generalization of that formula into n dimensions, and then using that as our definition of distance. Okay, so we should be thinking about this. This distance is the length of this vector, x minus y, where this is the definition of our length of that vector. And now with the notion of distance, we can just define convergence of a sequence in Rn. It's exactly the same definition as for R. So now when we have a sequence in Rn, that'll be said to converge to some element of Rn, or be Cauchy with exactly the same definitions as before. So if you actually look at the definition, it's not going to look any different. It's just that now your elements are living in Rn, and the distance, right, between xk and x is just interpreted as above. Okay, so sort of using that Pythagorean theorem measurement of the difference vector xk minus x. And basically the fundamental theorem here, which tells us we're not really doing anything all of that crazy, anything, it's not really that different than what we were doing before, is that a sequence in Rn converges if and only if all of the components of these elements of Rn converge. Okay, so we're thinking about these as vectors with n components, right, which are each real numbers. Xk is going to x if and only if, when I look at the ith component of xk, the ith component of xk is going to the ith component of x for each I. Okay, so that's an equivalent statement. So really when we're talking about convergence in Rn, we're just talking about simultaneous convergence of n sequences of real numbers. Right, so really this is just a fancy way of talking about simultaneous convergence of different sequences. So that's essentially the content of the next proposition. So the statement of the proposition is just what I said. If you have some vectors in Rn converging to x, that happens if and only if each of the components, or when I just look at the real numbers in the ith component, that those real numbers are converging to the ith component of x. Okay. And so the key to this, so I'll just sort of give you the idea of the proof. And I think I'll assign this for homework with this hint here. It's really not that hard. The basic idea for the proof is just to use a couple inequalities. So one inequality is that if we're looking at the square root of a sum of squares, let's say vi squared, that, well, the sum of the vi squareds, that's greater than or equal to any individual vi, right? So this is from I equals 1 to n. So the sum of the vi squareds, that's greater than or equal to the sum to any of the individual vi squareds. So let's say vj squared for some j. And then when we take the square root of that vj squared, we're just going to get the absolute value of vj. So we have that kind of inequality. So this is going to show that if you have xk going to x, okay, so if the length of the difference vector from xk to x is getting arbitrarily small, then each of the components has to be getting arbitrarily small. And in the other direction, if we have a sum of squares, then that is less than or equal to the square root of n times the maximum of all of the absolute value vj's. And that's just because each of these vi squareds is less than or equal to the biggest vj squared. Right? So you look at the biggest one, you say vj squared, then the vi squareds, each of them, you have n of these, right? They're all less than or equal to vj squared. So you have the inside of the square root's less than or equal to n times vj squared, and then taking the square root of that, you get square root of n times the maximum of the vj's. So that tells you that if all of the, so this inequality is going to tell you that if all of the components of the difference vector xk minus x are going to 0, then the maximum one has to also be going to 0, and that's going to imply that the the length of the difference vector from xk to x is also going to 0. Okay, so each of these inequalities, this one shows that if you have this limit in Rn, then you have each of the component limits in R, and if you have each of the component limits in R, then this quantity here has to be going to 0, and so the length of the difference vector is going to 0, so you have this limit in Rn. Okay, so that's the basic idea. You just need a couple inequalities, and the takeaway is just that, talking about sequences converging in Rn the way we've defined is no different than just talking about all of the components converging as sequences in R. So really we're not doing anything that's a crazy extension of what we did before. We're just talking about n sequences simultaneously converging in R. Now it follows quite readily from this that the Bolzano-Weierstrass theorem and the Cauchy criterion are both true theorems in Rn. Okay, so their analogs in R immediately imply. So the original theorem in R immediately apply the analogs in Rn, more or less immediately, not too difficult an argument to make. It's just figuring out how to make the fact that it's true in R translate into Rn, and that's relatively straightforward. And finally, the last little thing we need is to know that the triangle inequality holds in Rn. So defining our notion of length of a vector, sort of absolute value of an element of Rn. Instead of absolute value, we call it just the length. So the length of an element of Rn, it's the sum of it's the square root of the sum of the squares of the components. Okay, so just again, it's just the Pythagorean theorem. Then we have the standard triangle inequalities. They look no different than the ones we were using in R, except now we have elements of Rn and this sort of more complicated looking absolute value type function. So the absolute value of a sum or difference is less than or equal to the sum of the absolute values, and the absolute value of a sum or difference is bigger than or equal to the absolute value of the difference of the lengths. Okay, so this would be the triangle inequality and reverse triangle inequality. And the proof of that is a little bit more involved than in the case of the reals. I'll probably walk you through a proof of that, which is relatively uncomplicated conceptually in the homework. So for right now, we'll just take this as given. All right, so our first real bit of business is to define the notion of an open set in Rn. So basically, a set is going to be open. I was thinking open, like open, wide open outdoors type of thing. So the set's going to be open if there's always room, for any point to kind of stretch its legs, so to speak, inside the set. Right? So have some room to kind of move about a little bit, exercise itself. So in order to do that, we just have to define one preliminary notion. So that's going to be the notion of an open ball around a point. So let's make a definition here. So basically the idea is just a second. All right, so our idea here is that we have some set. And this set is in here, right? And so the set is going to be open if whenever we have a point, we can, it can give itself a little bit of room, right, where it can stretch out and move around. Okay, so as long as every point in the set has the ability to move around a little bit, it's going to be called an open set. And this little bit that it can move around, that's going to be just sort of a little ball or a little disc, just depending on the dimension. So in dimension 1, when we have our just real line, our set is going to be open if we can put some small open interval around it. So this is n equals 1, n equals 2 if you can put some little disk around it, n equals 3 if you can put some little open sphere around it. And so we first just define the notion of that open sphere, open disk around a point, and then we can define the notion of open itself. So our definition here is that we have the epsilon, so the epsilon neighborhood of X, or epsilon ball around X is the set, and X is an element of Rn, so this is the set. The book uses a different notation. I prefer this notation. So they use the letter V for whatever reason. I think it's more evocative to think about this as a ball around your point. So it's the set of all y in Rn such that such that y is within a distance of epsilon from x. So the distance between y and x is less than epsilon. And here, of course, epsilon, whenever we're talking about this context of a ball like this, epsilon is some number greater than 0. Doesn't necessarily have to be small. Context will probably dictate whether you want to think about it as being small or not. Okay, so that's the epsilon neighborhood of a point, so epsilon neighborhood or epsilon ball. And then follow-up definition, a set U is open if for every x in U there is some epsilon ball around x such that that epsilon ball around x, so this is the amount that x can sort of stretch out inside the set, so this is contained in U. Okay, that's the definition. So first, obvious example. First obvious example is Rn itself. So Rn is open since, well, we have to be able to put an epsilon ball around any given x in Rn, but of course, by definition, any epsilon ball, for any epsilon around any x is contained in Rn just by definition. Is open since b epsilon of x is contained in Rn for any x in Rn and any epsilon greater than 0. Okay, so all of Rn is open by this definition, which sort of obviously, intuitively, that should be the case. So another example. I guess we'll just get this one out of the way. It's kind of a weird example, but the empty set is open. So the phrasing of this definition is open if for all x in U, so basically whenever x is in U, it's the case that blah, blah, blah. So x in U implies that there's an epsilon ball around x, which is in U. But x in the empty set is false for any x, right? And false, let me say it this way. So you have, P implies Q is true whenever P is false. This is sort of just basic logic. Kind of the basic idea behind this, if you've forgotten, if this seems a little bit weird, just to recall, is that we basically sort of by convention decide to say that this statement is true when the statement's kind of not a lie. And the only way you can lie about this implication is if P is true but Q is false. And in every other instance, we just say that this is true, and so that's going to include when P is false. And so basically, if I start with a false premise, I'm not really telling you a lie because you're never gonna catch me in that lie because the false premise is never going to hold. So it's not really a lie there if you never observe that false premise and see whether Q follows from it. So anyway, this is basically called sort of vacuously true. This P implies Q is vacuously true when P is false. So the empty set is open since X element of empty set is always false. Okay. So that's not a really very substantive example, but here's a better example. So a better example is that these epsilon balls themselves, so we use the epsilon balls to define the notion of open, but that doesn't say anything about whether the epsilon ball itself is open. Okay, so B, so the ball of radius r, or the r ball around x is open for any x, and positive r. So we should justify this. So let y be, so let's say y. Well, let y be an element of this open ball. Okay, so this would just be an interval. When n equals 1, it would be a disk, a perfect circular disk when n equals 2, and it would look like an actual ball when n equals 3, and then kind of hard to visualize after that, but makes perfect mathematical sense nonetheless. Okay, so this covers the case of intervals when n equals 1, which is what the book is doing, but we have a more general thing happening here because we're working in Rn. So we have our y in this ball, and then what we have to do is say that there's a smaller ball, right? So this is our alleged open set U, and so we have to say there's a smaller ball around this y, which fits inside our alleged U, which is this R ball. And the idea for that isn't that hard if we just draw ourselves a picture. So we have our x, and this is our r ball here. So this is radius r. And if we have some y, what we want to do is try to fit an epsilon ball around that y, which fits inside that r ball. And it's sort of intuitively the case that we can go out kind of just this far, right? And go out till we sort of touch the ball there. And, well, where does that come from? Well, if we just sort of connect here, right, what we have is this. So this full thing is r, and this little bit here is the distance between x and y, right? So this here is the distance between x and y. The full thing is r. And so the radius of this red ball here should be big R minus the distance between x and y. So that's going to inform our proof here. Let y be that, then set epsilon equal to r minus the distance between x and y. So we claim that the epsilon ball around y is contained in the r ball around x. So let z be some third point, which is in this little epsilon ball. Okay, so z is somewhere in here. We want to say that z is in this r ball around x, so we have to say that the distance between z and x is less than or equal to r. So ultimately, we'll be measuring the distance between z and x. So here's z in here. So there's z, and we want to measure the distance between z and x, and what we can do that is just triangle inequality, measure the distance between z and y, and then y and x. Right, so we'll sort of overestimate the distance, and we'll see that that is less than r. Then the distance between z and x, the triangle inequality, that's distance between z and y less than or equal to distance between z and y and x. And the distance between z and y, well, that's less than epsilon, right, because it's in that epsilon ball. So this is less than epsilon. The distance between y and x is just the distance between y and x. And epsilon is r minus the distance between x and y. Right? And distance between x and y and x, same thing. So that just comes out to be r. And so indeed, the distance between x and z is less than r. So z is in the r ball around x, and that proves the proposition. Okay, so that gives us, now that we have our balls, our open sets, the next proposition tells us how to find other types of open sets. So we can use the balls to generate new kinds of open sets. So for instance, sort of intuitive that if we have this open ball here and we take another one here, that the resulting set is going to be, the resulting union set is going to be an open set. And also that the intersection of the two sets is also going to be open. And then the question is about sort of arbitrary unions and intersections. So it seems clear that if we keep adding more balls in here, right, that the union is going to be an open set. But it's not too hard to see that you can run into some trouble with the intersection. It's going to turn out a finite number of intersections. So like if you look in here at this little bit here, we have a finite number of intersections that looks open. But if we take an infinite number of intersections, so if we take, we say take a disk and then take another disk inside of it and another one inside of that and keep getting smaller, right? Those are going to zero in on a single point. And a point is not an open set. So we can run into some trouble if we do arbitrary intersections of open sets. So we'll just formalize that in this next proposition. I guess maybe as another example here, I should have done some example of sets that aren't open. So a simple example is that if you take a singleton set, this is never open. Right, since a ball of radius epsilon around x always contains points other than x. Points besides x. Okay, I mean, you can always take, x, say x, you can take x plus the vector like epsilon over 2, and then a bunch of zeros after that. Right, the difference between x and that vector is just has length epsilon over 2, as is easily computed. Okay, so now onto the proposition. So this is sort of a fundamental theorem about open sets. In a way, this is really the key property of open sets, so almost like the defining kind of property of open sets. So I'll write down the proposition. I'm just going to say that arbitrary unions of open sets are open and finite intersections of open sets are open, as we kind of indicated with our rough drawings before. All right, so we have an arbitrary collection of open sets, then the union over that arbitrary collection is open, and if we have a finite number of open sets, then their intersection is open. And we saw the pitfalls with if you even take a countable infinity of open sets, that the intersection might not be open. Your intersection could be a singleton set. So our proof is rather simple. So we take x, so let x be in the arbitrary union. And we have to fit an epsilon ball into this arbitrary union. Well, x is in a union, so it's in one of the sets. Then x is in u lambda for some lambda. Since this u lambda is open, there is a b epsilon x contained in u lambda. But then, right, taking the union, we're only adding to this u lambda. We're not taking anything away, so we're still going to have this containment. But then b epsilon of x contained in the arbitrary union is immediate. Okay, and so that proves part one. Okay, so I mean, the basic idea there, it's pretty intuitively obvious. If you have a bunch of open sets, you're only sort of adding to the openness, adding things on top of a particular open set. So you're not changing the fact that at any point you have an open ball in there. The intersection is different though, because when you're intersecting, you're kind of cutting stuff away, and so that could create some problems for your epsilon ball. You might have to take an initial epsilon ball in one of these U's. You might have to cut it down to be smaller to fit in this intersection. So we'll see how that works here. So let X be in the intersection of these UIs. Then X is in UI for each I. And therefore, there are B epsilon I around X, which are contained in the UI. Okay, so we have a different epsilon possibly for each of the UI. And what we have to do is find a single ball which is contained in all of these UI, and we have a bunch of different balls centered at X, right? But if we think about it, a bunch of different balls centered at X, it's just sort of like thinking in the two-dimensional case, just a bunch of concentric rings kind of around X, right? And so there's going to be a smallest one because we have we have only finitely many. And so we can just take the smallest one of these epsilon i's, and that one is going to sit inside all of the other balls, and so that will sit inside all of the UIs. So set epsilon equal to the minimum of all of the epsilon i's. Then the ball of radius epsilon around X that's contained in the ball of radius epsilon I for any I, and that's contained in UI, and this is for each I. So thus, B epsilon X is contained in the intersection of the UIs. Okay, so you see where this would fail in the this proof anyway fails in the general case. Because we can't pick a minimum if you have infinitely many epsilons. You can't necessarily pick a minimum. And you can easily see how you can arrange that there is no positive minimum. If these epsilon i's are going to 0, then you're not going to be able to pick a positive minimum. So the key thing is that all these epsilon i's are greater than 0, so when you pick the minimum, that's still greater than 0. Okay, so that's where the proof would break down. If we tried to prove the general case, which we already saw is definitely false by example. Okay, so that concludes that sort of fundamental property of open set. Okay, now I want to do another example of a set that's not open. So let's look at this example. So we're going to define the closed R ball around X. Okay, so it's denoted, so we have the open R ball notation here, and then we have a bar over it, and you'll see the reason for that notation later. So this is the set of Y in Rn such that the distance between X and Y is less than or equal to R. Okay, so the open, the normal R ball is just a strictly less than, so we allow less than or equal to here. And this is not open. And let's ask ourselves why. So the basic, again, the sort of intuitive idea is we have our R ball around X. At any point on the boundary here, sort of intuitive sense of the boundary, all the points where where the distance between y and x is exactly equal to r, that those points are not going to have an epsilon ball around them, right? No matter what epsilon ball we put around this y, it's not going to be contained in this in this set, right? So if this set were open, it would have to be the case that no matter which element of this set we took, we'd have to be able to fit an r ball or some epsilon ball around it. Okay, but so saying it's not open means we should be able to find some points where it's not possible to put an epsilon ball around there. So what we're going to do is consider any y such that the distance between x and y is equal to r. And so then we claim that the ball of radius epsilon around this y is not contained in the original set for any epsilon. And why is that? Well, if we put a little epsilon ball around here, right, what should we be able to do? We should be able to just go, sort of continue going in this direction just by a little bit, right? So this ball here has radius epsilon. See, my picture's a little bit small. But we should just be able to keep going in this direction. So say if we go like epsilon over 2, just continue in this direction from y, that should be a point which is outside of that ball. So consider, so to this end, consider z. So it's going to be, we're going to start at y and we're going to move out a little bit. So that's so z is equal to y plus, and we're going to move out a distance of epsilon over 2 in the direction given by the difference y minus x. So we're going to look at y minus x over the length of y minus x. That's sort of the unit vector in that direction. And so we have epsilon over 2. I'm going to have to erase this because I'm running out of room. Epsilon over 2 times y minus x over the length of y minus x. Okay, and then so now I don't think we need the picture anymore because we've gotten what we needed from it. So all we have to do is say that this z is in here, but it's not in here. Then, so the distance between z and y, well, the distance between z and y, this is just a unit vector, right? And this is just epsilon over 2. So this is just going to be equal to epsilon over 2. That's less than epsilon. So z is in b epsilon of y, but the distance between z and x, we want to say that that is greater than r, so it's further away from x than is permissible to be in that set. So the distance between z and x now, we can just compute this directly. It's y minus x plus epsilon over 2, so length, y minus x over length of y minus x. And that is equal to, I'll pull the y minus x out, so you have y minus x, and then 1 plus epsilon over 2. And y minus x in length is just r, right? So this is r times 1 plus epsilon over 2, and of course that's strictly greater than r. So z is not in here. Okay, and so that proves the claim that that set is not open. Okay, so there's no way you can Right, no way you can take a bunch of different balls and sort of union them or intersect them in funny ways to ever get this set. So when we think about a typical open set, maybe some kind of blob like this. Right, usually I'm sort of visualizing in R2. This is Rn, and we have our open set U. There are sort of all the points in the set, which we can always put a ball around, right? But there's these interesting points. There's a kind of boundary or something here in a general open set. There are points, so you have points here, which you can approach arbitrarily closely with points in U. Right, so you can take points in your open set and sort of take a sequence working its way to that point there. So this point is not in the set U, but it can be approached arbitrarily closely by points in U. And so we want to kind of formalize that notion. So for any open set, right, any of these points that you can approach with points in the open set are sort of obviously important. It's going to be an important notion. So that leads us to our definition. So basically what we're going to want to say is, right, so again, sort of have this picture that this point is a limit point of our set. Okay, so this point here is going to be a limit point. It's going to be a limit point if we can approach that point with elements of our set U. But the definition is going to say that as long as we can approach this point with points in our set U that are different from this point here. So I guess I should emphasize our definition is going to be for any set S. So this set might be open, might not be open. Okay, and so there's one scenario in particular in which this condition about being able to approach with points that are different than the point itself, and that's when, say your set S is like something like this thing here. Maybe it has some points along the boundary, maybe it doesn't have points along the boundary, and it has a bunch of sort of open points in here, but then it also has this sort of solitary point over here. We don't want to say that this point here is a limit point of the set S. Right? So even if this thing is in the set S, we don't want to say, well, this is a limit point of the set S because we can just use the constant sequence, right? That's just that single point over and over again, and we're sort of approaching the point here with just the point itself. We want to say we have a limit point when we can approach with other points that aren't just that point. Okay, so it'd be kind of weird to say this like isolated point over here was a limit point of the set S. All right, so that's what goes into the definition here. And so we won't need just one preliminary definition, which, again, is not in the book. I'm not really sure. I don't know. I think it's good. I think it's good notation to have this shorthand. So I'm going to define the punctured epsilon ball around X is, so we have B epsilon X, but I'm going to put a star there. Sort of imagine like punching a hole, leaves that star. And this is just going to be the epsilon ball around X, but with X removed. And another way to say that is that it's the set of Y in Rn, such that the distance between X and Y is less than epsilon, right? So you're in this ball, but you're not the point X itself, so it's bigger than 0. And then that leads directly into the main definition, which is that the point X is a limit point of the set S if the punctured epsilon ball around X intersects S for any epsilon. So if the punctured epsilon ball around X intersects with S is non-empty for every epsilon. Okay, so intuitively, we're just saying, so no matter how close you get to X, but are not X, right? So that's this epsilon, this punctured epsilon ball. So you're excluding X, but you're allowing yourself to get arbitrarily close to X without being X. If you look at the intersection of that with S, that's not empty. So you're always finding elements of S which are within epsilon of X. Okay, and that's, so it's a limit point. Right, so that's the concept of a limit point of a set. So as an example, we can take, say, S to be the set. So we have 1/2, 1/3, 1/4, etc. Union, let's say 2/3. So we have sort of 1/2, 2/3, 3/4, 4/5, etc. Right, then 0 and 1 are limit points. Are limit points of S since sort of this sequence here limits to 0. That means that whenever we put an epsilon ball around 0, we always have these points, some of these points in that epsilon ball, right? And none of these points are 0 itself. Okay, so actually it's in the punctured epsilon ball around 0. And then similarly with 1 and this sort of part of the set. Our limit points of S since 1 over n goes to 0, and n, let's send n over n plus 1 goes to 1. Okay, this is sort of just directly from the definition of limit. Right, that there's a definition of limit in the fact that these sequences don't actually coincide. The limit point isn't actually an element of one of these sequences. And so sort of obvious point to note from this that that limit points don't have to be an element of the set itself. Okay, so thus note that a limit point of S doesn't have to be in S. Okay, of course, a limit point of S may be in S. For example, if we take any open set, right? So any element of an open set, if you put an epsilon ball around it, that epsilon ball is contained in the set, right? So of course the punctured epsilon ball is going to intersect the set non-trivially. Okay, so limit points may or may not be in the set, and the terminology of limit point. Let's just prove a simple theorem that tells us that limit points. The reason for this is because a point is a limit point with in this definition exactly when there's a sequence in S which is tending to that point. Okay, so our proposition says X is a limit point as given by the definition above, if and only if, X is a limit of things in S, okay? And so it's a limit of things in S, and those things in S are not equal to X, all right? So of course, if X is in S itself, then you can always take just the constant sequence of X is going to X, but this is different than that, a little bit stronger than that. There's other elements of S which are limiting to X. Okay, so the proof of this shouldn't be that hard. Okay, so assume that x is a limit point. Well, if x is a limit point, then for every n, so remember, x is a limit point. That means that no matter what punctured epsilon ball we take around x, that's going to intersect the set S. So what we can do is we can take the punctured 1 over n epsilon balls. And so for every n, b sub 1 over n x star, the punctured ball, intersect S is not equal to the empty set. So there is some xn in that punctured ball, which is in S. Okay, so that means, so thus xn is in S, xn is not equal to x. Okay, so the first one, xn is in S, xn is not equal to x because it's in this punctured ball, and clearly, right, clearly it converges to x. It's getting within 1 over n, right? So for any epsilon, you just make 1 over n less than epsilon. And clearly, xn approaches x. Okay, and then the other way around, so we have this statement, so there's some sequence like this, and we want to say that x is a limit point of S. So we have to say that given some punctured epsilon ball, that there are elements of S in that punctured epsilon ball. Okay, so given the punctured epsilon ball around x, there is an n such that little n bigger than or equal to n implies, because what we're given is the convergence of this sequence here. Right? So we're given this epsilon, we can respond with an n such that when little n is bigger than big N, that implies that the distance between xn and x is less than epsilon. But then but this just means that the xn are in the epsilon ball around x, and we know that xn is not equal to x. So xn is in fact in the punctured epsilon ball around x. Okay, so that completes the proof. So I want to note here the bit about xn not equaling x. That's essential. So xn not equal to x is essential. So, for example, is essential because, if we take S to be just the singleton set X, so then the constant sequence, so we had this sequence X, 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 right? That sequence converges to X, of course, and all of the X's are in the set, but X is not considered a limit point of S. But X is not a limit point of the set, since we take the punctured ball around X, right? That set doesn't contain X, but then we intersect it with just the set containing X. That's equal to the empty set for any epsilon. So this situation, this X is called an isolated point of the set S. So in an isolated point, when you take the punctured ball around that point, it doesn't intersect any other points of the set. So we have a definition here. X in S is an isolated point of S if the punctured epsilon ball around X intersected with S is empty for any epsilon greater than 0. Okay, so these are points of X which are never limit points of the set S. Okay, so they lie in the set S, but they are nevertheless not limit points of S because there are no other points of S which are near them. And so this definition is kind of a warning. Just because a point is in a set doesn't mean that it's a limit point of the set. Okay, so just being in the set itself doesn't make you a limit point. You have to be near, sort of infinitely near other elements of the set to be a limit point. If you're not and you're in the set, then you're an isolated point of the set. Now the next thing we want to define is the notion of a closed set, which in a way is kind of at the opposite end of the spectrum of an open set, because you can kind of imagine, so if you imagine an open set being something like this, so it doesn't, and so an open set, like none of these points here are going to be in the set because points there are always intersecting the complement of the set. The balls around those points are always intersecting the complement. They're not contained in the set. And so we can, but if we start adding in these points, right, we start adding, and these are, right, so we start adding in these points which are limit points of our open set. Right? So we start adding in these points, and if we add all of them around here, right, so we add in all of that stuff, then intuitively we've kind of don't have any, then sort of intuitively this resulting set here contains all of its limit points. We sort of added in the limit points, and so there's no limit points missing. So we sort of went from this open set which had none of these limit points to adding in all of the limit points. So there's sort of like intermediate sets where you've added in some of the limit points, and then at the other end of the spectrum you've added in all of the limit points. And this is sort of roughly, this is analogous to in R1 just taking the closed intervals, right? And when you have a disk, sort of your open ball, and you add in all of the points, sort of open ball of radius epsilon, you add in all of the points at a distance of epsilon from X. So if you have your X and you have your distance epsilon, right, you add in all of the points at the periphery of the ball, then you sort of added in all of the limit points. That's going to be your closed disk. And so this will be the notion of a closed set. It's just going to be a set which contains all of its limit points. So that's the definition that we take for closed set. Sort of the idea of closed being that we've sort of closed up all of those limits. We've sort of taken all the possible limits from inside of our set and closed it off with respect to the notion of taking limits. So our next definition is a quite fundamental one. So a set F is closed if it contains all of its limit points. Okay, so intuitively, you sort of take a set and start taking all the possible limits and add them in, sort of close off your set with respect to the to the process of taking all limits, and what you should get at the end is a closed set, one for which there's no more limit points to add. Okay, so some examples here. So again, we have trivial examples. So Rn is closed. Rn is closed for the trivial reason that if we're talking about a limit point of Rn, so if x is a limit point of Rn, then x is an Rn. Just because, what else are we talking about here? We're always talking about the set Rn, right? This x is in Rn. So if x in Rn is a limit point of Rn, then x is in Rn, right? So this limit point is contained in the set. Okay, so this is just trivial. So that's kind of example one. The empty set is closed vacuously. And that's because since the statement that x is a limit point of the empty set would have to mean that the ball of radius epsilon around x, the punctured ball of radius epsilon around x, intersected with the set, which is the empty set, was not the empty set, right, which is false. And this is, I guess, for all epsilon greater than 0 is false. Okay, so for the same reason that that the empty set was open, it's also closed. And so what you can sort of note here is that sets can be both open and closed. Okay, so so note that sets can be both open and closed. So sets are not like doors, okay? So just because a set is open doesn't mean it's not closed. More substantially, the ball, so we take the ball of radius r around x, bar, right, which remember is, this is the set of y such that the distance between x and y is less than or equal to r. This is closed by this definition. So if we take z to be a limit point of this, so that there is a sequence yn converging to z, where the yn are not equal to z, this is by the proposition from above, and the yn are in the ball of this closed ball. So I guess I should just say a word about terminology. We just called this the closed ball just as sort of a descriptor, and now we have this other technical meaning of the word closed. So we're showing basically that we were calling this thing the closed ball because this is closed in the technical sense. So hopefully there's no confusion about why I'm calling this the closed ball before I actually have proved that it's closed. And okay, so now we just want to say that this limit point is actually contained in the set. And so to say this is closed means any limit point is contained in there. So what we have to do is measure the distance between z and x. Right, so the distance between z and x is the square root of the sum of, so we take zi minus xi squared, I from 1 to n, and we take the square root of that. But this is just equal to the limit as k, I guess I should say k here, since n is usually what we use for the dimension of our Euclidean space. So this is the limit as k goes to infinity of the square root of the sum. So we have the ith component of our yks. So yk's ith component minus xi squared. And so this is because, so since zi is equal to the limit as k goes to infinity of the ith component of the yks, right? So remember, we have convergence here in Rn when all of the components are converging, right? So the ith component of z is just the limit of the ith component of the yks. Right? So this zi here is just a limit of these yks, and then we can pull that limit out, right? Because this is just an algebraic expression, the squares and the sums. We can pull that out of there, and then we can pull that out of the square root by the what's it called? By a homework exercise that we did, right? The limit, you can pass the limit into a square root. And this is less than or equal to r by the order limit theorem. Right? So since each of these individually are less than or equal to r, so this is these are all less than or equal to r, and then the limit of a bunch of quantities that are less than or equal to r are also less than or equal to r by the order limit theorem. Okay, so here we have, since that and the algebraic limit theorem and a homework exercise about the square root, and then also the order limit theorem. So this comes down to a bunch of stuff we learned about limits just in R. So again, you want some talk about limits in Rn, just bring it back to limits of sequences in R. Okay, so that shows that z is within R of x, so z is indeed, so thus z is in the ball around x of radius r closure. All right, so our last thing here is we're going to talk about a proposition. So right now we have defined a set to be closed if it contains all of its limit points. And we saw that a limit point is a point which is the limit of some sequence of things in the set where the things in the sequence are not equal to the limit point. And so our next proposition just says we can drop this sort of annoying restriction here. So our set is closed when it contains, right, so whenever you have a sequence in F, the limit of that sequence is in the set F itself. Okay, so our proposition is that F is closed if and only if, when you have a sequence in F and it converges, that the limit is in F. Okay, so the proof is as follows. So let's suppose F is closed. And then there's two options. X is already in F or X is not in F. Right? So either X is in F and we're done, or X is not in F. But if X is not in F, then xn doesn't equal x, and so x is a limit point of F, but F is supposed to be closed, so we should have x in F, which contradicts that we suppose that x is not in F. Okay, so it must be that x is in F. And then the other way is basically immediate. So let x be a limit point of f, then right there's a sequence. Then there are xn in f, xn not equal to x, such that the sequence xn approaches x. But by our assumption, then by our assumption, x is in f, so f contains its limit points. And so f is closed. Okay, so that is our introduction to open and closed sets, and the necessary concepts surrounding those concepts. So we will discuss a little bit more about open and closed in the next lecture, but that's it for now.